In this section, it's section 17.4 out of the textbook, we're going to discuss traveling sound waves. Basically, we're going to come up with the equation that we can use to come up with the amplitude of the sound wave as a function of its position, x, and time, t. So if we envision our sound wave as a bunch of air molecules bouncing off of each other, and then there's basically a pressure which is applied, which then causes these pressure regions to move the sound wave with some velocity v. So it's going to be moving down this way in the x direction. So this will be x. And so what we want to do is come up with an equation for this oscillatory motion. So what's going to happen is there's going to be a sound wave, there's going to be an air molecule like right here, and then the pressure is going to come in and oscillate it. It's not going to push this air molecule and make it move all the way down the end. Instead, what's going to happen is the air molecule is going to go back and forth. It's just going to oscillate. It's going to bump into the next air molecule, which will bump into the next one, which will bump into the next one. So instead what we're looking at is a region of, say, total amplitude Sm, and you can go from minus Sm if this is x is equal to 0. And so the air molecule is going to oscillate back and forth, in this sinusoidal motion. So what we're going to do is we're going to take a slice in space of delta x, which is some distance s away from, we'll call the origin, x is 0, and we're going to see, what do we, can we come up with an equation for that? So we're going to start with an equation that says the position s as a function of x and t is going to be the maximum amplitude times a cosine of kx minus omega t. So we could use the sine function or the cosine function. It doesn't matter because sine and cosine are related by a 90-degree phase change. And if you remember, the wave number k is 2 pi over the wavelength, and the frequency, the angular frequency, omega, is 2 pi times the linear frequency, f. Okay, so now what we want to do is we want to relate this to a pressure, because that's what's causing the wave motion in sound waves is a pressure P. So can we rewrite this amplitude equation right here in terms of pressures instead? So what I'm going to start with is the definition of the bulk modulus, B, which is just the change in the pressure over the change in the volume over the total volume. And then there's a minus sign in there. So one way to start this is to say, well, let's rewrite this as the change in the pressure in our wave is minus the bulk modulus times the change in the volume over the total volume. So what is that change in the volume? What's the total volume? Well, the total volume, V, is just the area, if we go back, this area right here, A, times its width, delta x. Now the change in the volume is basically the area times, not delta x, because that's the total amount of air that we've considered in this slice, but instead a delta s, where delta s now is how much we're changing, let's say, the position here, like a delta s, right there. Okay. So now we have a volume, we have a delta volume. We can then put that into the equation for the pressure. So I get delta P is minus B, the area delta S over the area delta X. So the areas cancel, and I get minus B delta S over delta X. And if we want to turn this into a continuous difference instead of a discrete difference, then delta S over delta X becomes ds dx. So now our change in the pressure is equal to minus B ds dx. We have an equation for that. So delta P becomes minus B, the derivative of S max times the cosine of kx minus omega t, like so. Okay, so now if we perform the derivative, we have minus B S max, the maximum amplitude. Derivative of the cosine is minus the sine of kx minus omega t. And then we have to apply the chain rule, and I get another k outside here. So in the end, I have minus times a minus is plus, bulk modulus times the wave number times the total amplitude, and it gives me the sine of kx minus omega t. So what we could do is we could define a maximum pressure, PM, which is the bulk modulus on the wave number k, the total amplitude S sub m, and then rewrite this, or actually total change in the pressure. We're talking about changes in pressure here, not just the absolute pressure. So the maximum change in pressure I can get from these three quantities, and I can plug that into my equation, and I have the change in the pressure is the maximum change in pressure times the sine times kx minus omega t. So one thing I can do is I can play around with this definition now of the maximum change in the pressure and try and see if I can calculate that from other quantities. And so if you remember, well, let me just write it down. B, K, S sub M. The wave speed is the square root of the bulk modulus over the density. So that means that B is the density times the speed squared. So I could put that in. And I get the density, the speed squared, the wave number times the maximum amplitude. Now we could play around with this a little bit further and say that the speed of the wave is also the wavelength times the frequency. And the wavelength we said is 2 pi over k. And the frequency is omega over 2 pi. So I could rewrite this as omega over k. So omega then is k times the wave speed. And if you look in this equation I wrote above, that the wave speed times k is omega. So, I mean, I don't know if it really makes much of a difference, but you could also figure out that the maximum change in pressure in our sound wave here, we could write as the density, the velocity, the frequency, and the maximum amplitude. So you can write it in those quantities too. You know, six one way, half dozen the other. Which one you want to use, it really just depends on the problem that you're trying to solve. But the key is here, well, there's a couple of things, a couple of key notes to discuss. One of them is that if I go all the way back, we solved this amplitude, where the air molecule is going to be at any position in time, as a cosine. And the interesting thing is that the pressure now is the sine. If we had defined the other one as the S as the sine, and the pressure would come out to be the cosine. So the change in the pressure is basically 90 degrees out of phase with the amplitude. So the other is that if I look at the maximum change in pressure, there's a lot of quantities that I can play around with. One, I can change the density, and that kind of makes sense. If I change the density of the material, the pressure applied to it is also going to change, and they're all kind of tied together. It depends on the speed of the wave in the material, and basically the maximum amplitude. So I could turn this equation around and say if I want to find the maximum amplitude of my wave, I would have to measure the pressure, measure the density, know the speed of that wave in that material.